record. Okay, so we are continuing with what we ended last last lecture. And last lecture we actually were talking about Bowman credibility, and we finally finished with the prerequisites to that. So we are ready now for solving this task example 5. This one is quite comprehensive. So it involves three calculations with claim frequency, with claim severity, and with aggregate loss. So this one, actually, let me open the task. So we are ready to start with the claim frequency, and let us make the whole let us make the whole task appears as in the form of a table, and we will calculate the columns from that table with R, and this will be quite useful and quite easy for us. So let's okay, I don't need to open anyone else. Okay, so the first one, let's create the new the first thing which we are going to calculate. According to our information, the new is just the a combination of the frequency times lambda. So our mu will be 0.2 times 20 plus 0.4 times, okay, do you video 0.4 times 30 plus 0.4 times 40. So this one is actually mu, and our EPV, the thing which we are going to calculate, 0.2 times actually the same kind of calculations, but with the squared components, 30 squared and 40 squared. This will be the EPV. The final thing that we need to calculate is called the sigma, actually sigma squared, the variance of what we're trying to understand, and the variance will be sigma squared. Okay, hold on. Okay, maybe this will be better. Okay. So our sigma squared actually is EPV minus mu squared. Okay, mu is created. Yeah, sigma squared. This is just the name. So this is sigma 2, and sigma 2 is our 56. Let's check what is mu, and mu is 32, and EPV is 1080. So we are first created the prerequisites for the first task for claim frequency, and actually we can create something with the table, right? So let's first check what will be the total. The total will be mu plus sigma squared, and this is the total variance. As you remember, the total variance of n is 88. So now let's go to claim severity and create the table here. So the table will be appeared as the tab. This is our task B. Claim severity. If you understand that severity is how hard the claim is, So how much money the company will need to pay for the one particular claim. Okay, so claim severity has three groups. So here we have 1, 2, and 3. These are three groups. These are three groups. Okay, do you see this example? The slides and the RStudio. Okay, so our table will be the data frame, and to create the data frame, actually we need three types of data. So let's say first will be group, then will be the frequency, the group probability, then will be lambda. This will be the parameter, right? So let's just create group is the 1, 2, and 3. Connection is unstable. Okay, 1, 2, and 3. Then group probability, group P, will be the vector of these values 0, 2, 0, 4, and 0, 4. Okay, and our lambda is the 20, 30, and 40. So again, this is the vector of 20, 30, and 40. Okay, so group P, and lambda. So the table will be the data frame of these three values, group P and lambda. Okay, and our tab actually is the prerequisite for this, how to say it, for our initial data, and then we are going to create additional columns in this table. So let's say the new column is created with the $sign. Let's say the column which will be calculated as the multiplication of column 2 and column 3, and this will be the tab of our group P times lambda, tab lambda. So it is the vector operation. We just need to specify the single operation multiplication, and it will be use the two vectors there, and everything will be fine. So our tab right now is comprehensed with the extra column C2, C3. Okay, so now this is just the multiplication. Next thing, we need to calculate the probability of severity. Let's say the probability of severity is the vector. We just need to create the empty vector in order for us to place values inside that in cycle. Okay, the cycle 4 from each of these groups, for 1, for 2, for 3. So the probability of severity will be placed the values which are calculated in the cycle. Okay, so we are creating the vector, and the vector will be of the type of double, and the length of this vector is 3. So probability of severity is just these 3 zeros which are created here. And now we will replace those zeros with the actual values, and for cycle 4i in vector from 1 to 3, then our probability of severity I will be tab C2, C3, the particular value inside that column. So we will take this value, for example, and divide by the sum of all these values. Then we will take this value and divide by the sum, and then we'll take this value and also divide by the sum. Sum of tab, and we place the C2, C3 here. Okay, so this is it. This is our calculation in cycle, and once we complete this calculation, then the probability of severity is just these numbers. And let's add those values inside our table as well. So we will just use the same name of the column, and this will be equal to probability of severity. Okay. So once we done that, our tab will be comprehended with the probability of severity column inside. So everything is all right. We are sharing. We are more recording. Okay. So this is the first option, the calculation of probability of severity. Okay, then what else do we need to calculate? Actually, we need to calculate a couple of conditional conditional probabilities. Let's say that we will need to calculate the conditional mean. First of all, this will be the mu x, the conditional mean, and then we'll need to calculate the conditional variance, variance x. And these will be almost the same as we have calculated here, our mu and c, all right? So to calculate that, let's define, let's say mu x will be actually we have the parameters here, alpha and beta are given for each of the column, these are they. So mu x is just the product of alpha and beta, okay? So mu x will be 5 times 2, 4 times 3, and 3 times 2. So I'm just multiplying 5 times 2 for 3 and 3, 2. So there is a vector of 3 products there. And the variance of x is also these calculations, but we will add the square to the right-hand side as the same kind of calculation is performed over here. Okay, so this is the mu and variance. And actually our tab will contain 2 extra columns. So our table mu x will be mu x, and our table variance of x will be variance of x. Okay. So this is the table, and we can see these whole computed values inside our table. So what actually do we need to calculate then? We need to calculate the EX, and EX will be calculated with our 0, 1, 25 times 10, then product of that, and then product of that. So this is the sum of those products. So conditional mean mu x, conditional variance var x, and these are corresponded to these three severity, three different distributions of claim severity. So EX, let's start with that. EX will be, let it be like that, the sum of tab probability of severity times mu x. This is it. So this is our EX. Then, as we specified, we need to calculate the mu PV, and the mu PV is the sum of tab, again, probability of severity, but we multiply on variance, like that. So EX is 875 and mu PV is 22. All right, after that, we need to calculate the DHM. Like in the previous lecture, the main point of interest is to calculate the total variance, and to calculate that, we need partial of that, the mu PV and sigma squared HM. So sigma squared HM, sigma to HM, let it be like that. So it will be E mu X minus E squared. Okay, so E, actually, do we have E anywhere? We don't have it. Okay, then where's our E squared? That's kind of interesting. Okay, so this will be E mu X is actually, it is also not defined so far. Let's calculate the E mu X first of all. So this will be the sum of probability of severity times squared value of mu X. So this thing squared, and this will be E mu X. Okay, 84.5. And the last thing is just to understand what the value of mu is. And the value of mu should be just EX. So this will be EX squared. This is 875. So our 84.5 minus 875 squared, this will be something less than 8,79375. So therefore, we have calculated the second component of our total variance, and the final answer to the second part, to our part B about claimed severity X, is that. So total is the sum of mu PV plus sigma squared HM. And the total variance is 29,9375. Okay, this is the second part of our comprehensive task. So I'll just make that in order for you to be able to copy. So you may have a screenshot of that. And the third part of this task, we need to calculate the aggregate loss. So the distribution of the aggregate loss S is determined jointly by our okay, something happening with the video. I'm not sure why it is start. Okay. The aggregate loss, the distribution of the aggregate loss S is determined jointly by L and G. Actually, the G is what we have been calculated over here. This is the conditional X given G. This is conditional variance X given G. And we shall denote this aggregate loss as theta. Theta is this parameter given like that. Theta. This thing. Okay, so for the conditional mean of S, we will have the combination of lambda times alpha times beta. And for the conditional variance, we will use the result on a compound distribution for Poisson-Klein frequency. And the variance will be, okay, let me first of all define the expected value S given theta. This will be lambda times alpha times beta. So this option, lambda alpha beta. And for variance, it will be a little bit more complicated given theta. It is just the lambda times alpha beta squared plus alpha squared times beta squared. Okay, let me close the bracket. Close the bracket. I'm not seeing my mouse. And dollar here. So this is the value which we need to calculate. The alpha value, which is just the multiplication of 3 parameters, and variance, which also can be calculated because we have all the lambdas, alphas, and betas here. So our EX, open new option. Here EX now is the 20 times 5 times 2, this the first value of EX, this is just 200. So we calculate again 3 values of EX, and the second one 30 times 4 times 3. Then the third one will be, let me make it a little bit more compact. And the third one is 40 times 3 times 2. So I am doing just calculating the formula lambda, alpha, beta. The parameters are given here, so these are they. And now the variance X is okay. This is a little bit more complicated. So lambda, let me open. So 20 times then alpha beta 5 times 2 squared plus 5 squared times 2 squared. So this is the first parameter. Let me check whether it is. So the first parameter is 2400. Then let me so next again, let's just copy and change that. This one, and the third one is here. So the third one here is 40, 3, 2, 3, 2. Here is 30, 4, 3, and 4, 3. Squared and 3. Okay, so this is the variance. The variance contains with 3 values: 2400, 5400, and 1920. Once again, how can we calculate the this kind of ES? Okay, so the S is the aggregate loss, and we have to calculate ES. Let it call it right that. And actually, the calculation should be something with this form. So we need to just have another tab. Well, let's say our tab contains the probability. So let it be tab 1. This is the data frame. For group, we need group P, group probability, and then we will implement the EX and var X. So to make just sure, this is EX and this is var X over here. So our tab 1 contains now with these values inside. So what we need to do, we just need to calculate the multiplication of group P and EX. So ES, this will be this tab 1 group P times tab 1 EX. So this is the value of ES. Okay, so this is the value of ES, tab 1 EX. Do we have it? 0 to y 200 and 200 and 200. EX should be recalculated. EX or ES. So tab 1, yeah, new values, and ES is 280. So 280, this is the correct thing. And also we are ready to calculate the EPV. This is the same sum, but instead of EX, we will include this variance inside. So this is EPV, the first component of our variance, and it equals to 3,408. The final calculation is just the VHM, or sigma squared HM, and sigma squared HM will be the we have been calculating it with those values, mu, let's say S sigma. No, let us maintain the same thing. So group P, tab 1 group P times mu x squared. Okay, let it be E mu x 92, right? 92. And then we will calculate the ES squared. This is actually, we need to calculate something with a squared value here. Squared. That's not good, actually. Mu x tab. Oh yeah. Oh, sorry, tab 1. Yeah. ES tab 1. So ES is, let me check those values. So ES is 280, and that's correct. So we will subtract the squared value. This is correct. Then here E mu x. So we will multiply tab 1. What is our tab 1? We will multiply 0.2 times tab 1. Tab 1 doesn't have mu x squared. Yes, this is the problem. So the tab 1 has EX parameter, EX squared. So this is it. And our sigma squared HM has a really big value. Why is that? E mu x 82,000 and ES squared is 78.4. So we don't need to square because we haven't squared previously in that E mu x. Okay, so we don't need to square here. Yes, so this is the value which we were looking at. The calculations should be performed in this form. Everything is stated on the slide. So this is actually sigma squared HM. This is the second part of the component of what we need to calculate. EPV is the first part, sigma squared HM. This is the second part, and the total again, just the sum. Total is the sum EPV plus, which is 3,408 plus that sigma squared HM. Okay, so our total is this value 7,888, and this is the value which we're looking at. So EPV and VHM, once again, they measure two different aspects. Okay, measure two different aspects of the total variance. When a risk group is homogeneous, so that the loss claims are similar within the group, the conditional variance is small. So if all risk groups have similar loss claims within the group, the expected value of the process variance EPV is small. And we also can define the value of parameter of K. Actually here, the K will be the coefficient of mu PV divided by sigma squared HM, or here in our case, this is just the relation of sigma EPV and sigma squared HM. And the value of K is, let's see, is 0.76. So a small EPV, EPV is a numerator if the EPV is small, or if the VHM is large, that will give us the small value of K. The risk groups will be more distinguishable if the mean, in the mean when K is smaller. So we are trying to make the comparison between in-group variance and within-group variance. So this will be the relation of that. And the groups will be distinguishable if EPV is smaller. Okay, so any questions here so far? We have just calculated the three measures: the claim frequency, claim severity, and the aggregate loss of our three measures. Claim frequency, and this is our claim frequency. The variance of claim frequency is calculated with that thing, and total here was 88. This is the claim frequency total variance, and the claim severity, it was like that, and the total here was 29,9375. And finally, we have calculated our variance of aggregate claim loss. This is the variance of aggregate claim loss. So a really complex example. We will use this kind of example in our exam. So next lecture, we will just put some more emphasis on what we're doing there, solve several tasks, and you'll be ready for your exam. So next thing, if you don't have any questions, then we could continue with, so this is the K value, which I specified over here. So it will be easier to distinguish between groups if the variance of the hypothetical mean is large and the average of the process variance is small. So EPV is small, VHM is large, easier to distinguish between the groups. Okay, so now we are going to solve example 6, and then we'll have a break a little bit. So example 6, what do we have here? Frequency of claim per year is distributed as a binomial random variable with 10 and theta values, two parameters of binomial, binomial distribution, and claim severity X is distributed as an exponential. So let's move on to specific values of that theta. Okay, so what can we do here? Actually, we are ready to create another table. This is example 6. So our step 2 will be the value of let's say theta is the vector of 0.3 and 0.7, which is given in our task. This is it. Then the probability of that theta, again, these are just binomial random variables, so 50% probability given that. And then we will be able to calculate the probability of, let's create first the table with those parameters with theta and probability theta. Okay, so these are our table, data frame. So the table is like that. Now we may calculate the squared, the cubes, and the fourth moment of our, not the fourth moment, but the fourth power of our probabilities, and then we will calculate the expected value for our required moments. Okay. So the final calculation should involve calculating this key. Okay. So tab 2 and then probe theta 2 will give us the that probe theta squared. So this is our squared values. Not the probe theta, but the theta. Sorry, theta and theta. Okay, so this is our theta, probability theta, and tab 2 theta is theta. Yeah, I've spoiled a little bit. Okay, once again, this, and that. Then theta squared is the theta squared. So this will be our correct version of the table. Then we will calculate the 3 and 4. 3 and 4. This will be cubed and fourth power. So this is our tab with the calculations. All right, now we are ready to make the calculation of required moments of this parameter. The first of all, we will calculate the expected value, and let's say E theta will be what? The probability times the parameter. Tab theta times tab 2 probability of theta. So this is our expected value, and let's make the sum of those, and we got the single value, which is 0.5. The same kind of thing will be applied to our second, third, and fourth. Second, third, and fourth. E theta 2, 3, 3, and 4 over here. Then we will use theta 2, 3, and 4 over here. So this is our calculations. Okay. And let's say that E theta 4 is 0.1241. So if you are able to follow me, then you will have the same kind of results. And finally, we have found everything, and actually we can calculate the k value, and k value, while actually we were doing everything that, this is the fraction of mu PV, PV over the sigma squared of our HM. So this is the value of k. Again, I hope you can see this thing. This is 2e theta cubed minus E, make it to the center of the screen, minus E theta to the power of 4. And this is actually the fraction. Numerator and denominator is 10 E theta to the power of 4 minus E theta squared, and again squared. Okay, hold on. I have missed this squared. It should be over here. So this whole thing is the actual value which we need to calculate for our k. That's why we have calculated E theta cubed, E theta 4, and E theta squared. So let's implement this kind of formula and just calculate what we have here. It will be much easier to just place k equals to 2 to the power of, okay, I just need the values which we have here. So we will need E theta cubed, then we subtract the E theta 4, and this is the numerator, really easy, and then 10, this is the just coefficient 10 times E theta 4 minus E theta squared, and this thing should be squared like that. Okay, and if everything is correct, then the key value should be defined like that. Is everything correct or not? 2E 10 E theta. Yeah, okay, so 10 E theta. We have to maintain the brackets over here. Yeah. So key value is 0.61475. Okay, we have just calculated the parameter k using the required moments. And if you have something really easy like the binomial distribution, where you have where you know these probabilities, then everything should be fine. You will be able to find the expected values and just maintain the squared, cubes, and fourth powers, and then recalculate the expected value of what will be the probability of theta squared, the probability of theta cubed, and fourth, in order to calculate k using this kind of formula. Okay, so note that both EPV and VHM, they depend on our parameter. What was the parameter? It is the parameter C. However, as the effects of C on those components effects are the same, the ratio of EPV to VHM is invariant to C. So actually in this formula, we don't have any C parameter here. So once again, the both EPV and VHM, they depend on C, but the K doesn't depend on C. So this is the first part of our lecture. If you have any questions, please let me know. And we will have a break, returning at 10:40. Okay. Using the code. All right. So for now, when we completed this option, we are ready to move on to our Bowman credibility. And actually, there are several things we might Yep. So which we might use. Actually, this is the formula, the final formula, which is really important for us. This x, next value of x depends on the mean value of x and the mu value of x, and with the z. Z is the credibility factor, which we are going to consider really important. So Bowman credibility factor, or just simply Bowman credibility. This factor Z, it depends on EPV to VHM ratio K. As you can see, this is the ratio K, which we were just calculated. And this, how to say it? K here is the Bowman credibility parameter. Okay. And generally, the formulas are more or less the same EPV, the same VHM, the same total variance. K is just the difference between mu PV and sigma squared HM, which we also have been using. And the new thing is just the Z, which is placed inside the formula for our XN. And then, once again, these are the same formulas like on the previous slide. So Z is the Bowman credibility factor, or Bowman credibility, and K Bowman credibility parameter, and the forecast for the next value of X is called the Bowman premium. So we just will calculate the Bowman premium as a linear combination of mean value and the mean value for X using this Z parameter. So what else can we say? The K depends only on parameters of the model, and Z is a function of K and the size N of the data. So this is the how many data points we have. For predicting claim frequency N, the sample size is the number of periods, right? The number of periods for which the how to say, the number of claims is aggregated. So for predicting claim severity X, the sample size N is the number of claims. As aggregate loss S refers to the total loss payout per period, the sample size is the number of periods of claim experience. So this is what we can say about the theory here. And again, our example 5 is the complex example which we were calculating these tables. And suppose the claim experience last year was 26 and the average claim size 12. So we need to calculate those three values. Let's do that. Okay, so for our example 7, what was the value of K in our example? So let me move back. 29, 98, I was recalculating. And the value of K, no, I don't see it. Okay, let's recalculate. These are the parameters which we might have used, and K is the value 0.76, right? Why 0.76? Maybe we'll have something different. This is for aggregate loss. Okay, this is for aggregate loss. For claim frequency and for claim severity, the values of this parameter K will be different. Okay, let me refresh what we have here for claim frequency. Okay. So EPV divided by sigma squared here. No, that's not correct. We have to calculate the EPV, which is the sum. Okay, EPV, which is the sum. of that. All right, we won't bother. I just place the formula is the same, like 0.76, but I'm just remembering that for our claim frequency parameter, it should be 0.575714. For part A, for part B, it should be, again, I have to remember, this is the 2.70 equals 2.7717. This is for part B, and for part, the last one is that, let's say, for the last part. Okay, so we have all these three parameters now. We are caring about the new values which came, the claim experience 26 and the average claim size. Okay, as we remember in our first task, in task number 5, our EN, which is actually the M equals EN, this was 32. And we are given that N equals 1, and we are given that D equals 26 from here, the experience from last year. So now we are ready to calculate the credibility factor, the Bowman credibility factor, 1 over 1 plus K. So if K is this value, then Z will be 0.63, and the updated credibility will be Z times 26 plus 1 minus Z times 32. So 26 is the past experience, 32 is current experience, the value of Z which was calculated, and we are ready to say that the frequency, the updated prediction of the claim frequency or forecast for the claim frequency for this group is 28. So previously it was 26, now we are forecasting it as 28, and the actual is 32. So more or less we can stick with the value of U. The same thing can be used for claim severity. For claim severity, our M, which was EX, which was 875. Our N was 26, D 12, and the Z parameter is 26 over 26 plus this parameter K plus K, and our Z parameter is 0.9. So once again, the same kind of formula for forecasting, and instead of 26, we use 12 for average claim size, the previous average claim size. The current claim size is 8.75, and the U value for claim severity is like that. This is it. The previous one was here. Okay. This is for claim frequency. This is for claim severity. Okay, and the last thing is for the S, for aggregate loss. Let's compute for aggregate loss. M, in our case, M is ES, and this is 280, N is 1, and D is 26 times 12. This is 312. So we have the value of z of 1 over 1 plus the current value of k. This is and the current value of u will be this u times 312 and the current value 280. So u will be u will be almost 300. This is for aggregate loss. So we have used the Bowman credibility to calculate the values, the forecasted values of the claim frequency, claim severity, and the aggregate loss based on what we have experienced last year and based on what we are expecting this year. So these are the forecasts. Any questions here? Okay, so next is example 8. And once again, we are referring back to our example 6, which was, this is 7. This one is example 6, okay. And example 8. Okay, what do we have here? Number of claims in the last 3 years were like that. Corresponding average amount of claim like that. So calculate prediction for aggregate loss. If we were given the frequency and severity, our aggregate loss is just the multiplication of those frequency and severity, and everything should be fine. So just to maintain the record that we have 3 years of experience, so we will have to divide 1 over 3, and then will be the just simple calculation. 8, 4, 7, 12, 19, and 9. So frequency, claim frequency is the vector of 8, 4, 7. Claim severity vector 12, 19, and 9. And this will be like claim frequency times claim severity. So these are the values, and we just need to sum those values. And this is the value which we are looking for. So we first calculate the average. This is the average aggregate loss per year in the last 3 years. So on average, we were losing 78.3 something units of currency or something like that, maybe $1 million. What is the key value? Once again, we need to refer to example 6, and key value in that example was calculated as 0.61475. So we have this key value. K equals to this value. And what can we say? I am reminding you that it doesn't depend on C value. And as there are 3 observations, how to say it? 3 observations of our aggregate loss, the Bowman credibility factor will maintain these 3 observations. So it will be 3 in the numerator, and it will have these 3 on denominator. So Z will be 3 over 3 plus K. Okay, so K. Z factor is 0.8299. Now, what is the unconditional mean of aggregate loss, and how can we find the value of C. So we have to calculate the updated prediction for these C values. So we need to somehow place C inside those formulas. And to do that, we can use the let's say EES of theta. And we know we have to use the coefficient 10, and then we need to use the expected value of theta squared. So what was our expected value of theta squared? 10 times that. So the EES will have 2.9, and we know that this is 2.9 times C actually. So there is the virtual parameter of C over here. So using this equation, we will place EES as inside this formula. So we will have to place Z parameter is calculated. This is it. X bar is what is the X bar? What is X bar? Okay, we don't know yet. Mu X is what we just calculated. This is 2.9 C. So let's refer once again to example and find out what is X bar, what our table states. Table states then E theta. What is our E theta? 0.5. Our key value. So how can we? We should have been calculated that. We should have been calculated that. Claim frequency times claim severity. This is our result, right? So the sum of those and the average claim size, this is 78. Yeah, so this thing, let's call it X bar, X, EX, this thing. Okay. So now we have everything to calculate, and then we will just place in place the two values of C, C equals 20 and C equals 30 inside. So Z times EX plus 1 minus Z times EES. Okay, this is C, when C equals 20 times 20. So this is the value of Z in the first case, and 30, this is the value of not the Z, this is the value of the prediction, 74 and 79 when there are two parameters. So what we have done, we have derived the Bowman credibility prediction, not the prediction, predictor for future loss as the linear predictor in X that minimizes the mean squared prediction error in the equation. So actually the Bowman credibility is everything about MSE, the mean squared error, the minimization of this mean squared error. So our formula for the prediction is using the MSE inside. So we also consider the problem of a linear estimator in X, which minimizes the squared error in estimating the expected future loss. So our E of mu minus model value of mu squared, and this mu n is just our mu x, and the next value is a linear estimator of the next value, and we just using this Bowman credibility predictor for future loss and Bowman credibility estimator for the expected loss, and we can interchange them actually. So everything is everything again, when we try to explain it and try to implement the formulas straightforward, this should be not hard actually. So the value of C, just remember that actually the value of C is over here, so it should be virtually times C. That's why we have this 2.9 times C. That's why we implemented the given values of C inside our formula and give these two predictions. And the answer is 74 and 79. Okay. So this is it for Bowman credibility. And now we are going to use the more important maybe thing, or maybe more advanced technique, the Bowman-Straub credibility. So the main, the critical thing that there are different distributions. They are not identically distributed. So loss observations are different. And because we have been using Bowman credibility as a linear estimator, we were assuming that all the losses were identically distributed. For Bowman-Straub credibility, we say that they are differently distributed. So the formulas also will be almost the same. Nothing actually changes that hard in our calculations. So what we have here, the E is the same mu, variance is the sigma squared by divided by m, and the expected value of variance mu again divided by m, and we form these predictions. So to calculate these predictions, we need to estimate what will be the coefficients of beta 0, beta 1, beta n. Okay. So x should be given to us, and we need to just estimate the coefficients. And this, again, we are using the least mean squared error predictor to estimate them. And in order to estimate them, the betas will be calculated with this kind of formula. Seems quite complex, but actually that is not. K again is the same value. Z, instead of n, we just place m, saying that there are different distributions, not the single distribution. And beta 0 is special case. It can be derived as mu x minus mu x times beta s. So it is just 1 minus z times mu x. And again, we are coming back to the same kind of formula for x. So if you know this single formula, it can be applied both for Bowman and for Bowman-Straub credibility as well. Okay, so I'm again assuming that it's better for us to just solve tasks, not just to be overwhelmed with the math behind that. Okay, so let's start with example 9. These are the examples which will finish our total course for risk and insurance. This is the last topic which we are going to cover, the Bowman-Straub credibility. So the number of what we need to calculate. We need to calculate the prediction of the number of claims in the 4th year. So we need to just calculate this empty value inside the table. So let's do that. First of all, we will again having that the binomial random variable is given. So we have 0.5, 0.5. Claim incidents are independent across insureds. That option states both for Bowman and for Bowman-Straub credibility, the independency, but identical distribution is different. So the probability that binomial has a beta distribution with these parameters, and okay, let's try to solve it. Okay. First of all, let mi be the number of insureds, this value number of insureds. Let's then x, this xi, these are claims per insured. And what else do we need to find? We need to understand that our EX, our value of expected value of xi given given value of theta, conditional mean is 2 times theta. So this is the 1 over m, the sum of xi j given theta. This will be just 2 times theta. The first point. And the second point is sigma squared hm. Squared hm. This thing is actually the variance of our 2 theta. And given that, we have the 4 times variance of theta. So this is the parameters if we talk about binomial distributions with parameters 2 theta. Okay, Bn 2 and theta. So this is the expected value and the variance, 2 theta and 4 variance theta. Then if we are talking about beta distribution, and we have the parameters alpha equals 1 and beta equals 10, we have the variance of that distribution, variance of theta. And this is just a fraction alpha beta as the numerator and a little bit more complex alpha plus beta squared. This one. Alpha beta squared times again here alpha plus beta plus 1. So this is the variance for our distribution beta. So what can we say here? We have these parameters alpha beta here, they are given 1 and 10. So variance of theta parameter can be calculated instantly. This is just in our case, this is just 10 divided by 11 squared times 12. So just given the parameter theta, and this is, okay, let's calculate. The parameter is 0.068. Okay, so we have calculated the variance of theta. Okay. Next, what do we need to calculate? For the conditional variance, the expected value, okay, let's move. Then conditional variance, variance of x theta is the fraction. And first of all, we have 2 theta 1 minus theta over here, and then mi over there. So from this conditional variance, we can extract mu PV, and mu PV will be just the 2. Okay, let me write down mu PV. This is 2e, then theta 1 minus theta. Okay. Like that. And from that, we are able to extract E theta. And E theta, given that we are talking about beta distribution, is really easy. These are just the fraction of alpha and the sum of alpha and beta. So again, we are ready to calculate that instantly. This is 1 over 1/11, and 0.009 should be something like the result, 1 divided by 11. So this is the value of expected value. Okay, so this is the expected value. Once we obtain the expected value, we move to mu PV and we calculate this mu PV. Mu PV is 2 times our 1 over 11, then minus this variance, plus 1 over 11 squared. So if everything correct, then the PV should be something 0.1. No, it's larger. Okay, let's then recalculate and place that EPV. EPV is like that. Variance var PV is like that. 2 times EPV minus plus EPV, variance over here, and we should place the bracket after that. So once again check. Yeah, so mu PV is 0.15. So this one is correct. Okay, so we have calculated mu PV, and again we are moving back to what we have stated with the K. K parameter is mu PV on the top, and the sigma squared HM. What is the sigma squared HM? This is stated here. This is 4 times the variance. Variance is given, so we divide it by 4 times our variance PV. Okay, so K value is 5.5. Then now we have the number of insureds, and we are ready to calculate the Z value over here. M is the sum of 100, 200, sum of the vector 250, 280. So we will calculate like that, and is 830. Okay, hold on, we don't have the number of claims here, so we will not be using 180, so the M is just 550. Okay, given that Z is M over M plus K, so Z credibility parameter is 0.99, almost 0.1. And what else should we calculate for our result? We should calculate mu x, which is 2 times EX, 2 times EX, not EX, but EPV over here. Okay, this one is mu x, 0.18 x bar is the number of claims. sum of vector 7, 13, 18. This is x bar 38, and we divide that x bar over how many, over m. So I'm just using the same kind of formula, the formula for our the expected variance, where we divided mu over that. We also will be calculated the x bar, and the x bar will also be divided over m. So everything in the Bowman-Straub credibility is divided by m. So here we also divided, and x bar actually is this small value 0.0069. So we are ready to calculate the predicted number of claims for our year. Z parameter times x bar plus 1 minus z parameter times mu x, right? Times mu x. So this is it. This is the result, 0.07. Now we are answering the question: calculate the Bowman-Straub credibility prediction of the number of claims in the 4th year. So what will be the number of claims when we have this credibility factor given that 280 times this value? Okay, and this is the predicted number of claims, 19.66. This is the predicted number of claims. Okay, this is it. Now we're going to the break. We'll continue at 11:30. If you have any questions, please let me know in chat. Okay. So we have calculated the predicted number of claims, and now we are ready to solve another task, another example for Bowman and Straub credibility option. So the number of accident claims per year is a Bernoulli, a random variable. We have given the probability theta, different values. Okay, and once again we need to calculate this how many will be the total claim amount, how much will be the total claim amount. Okay, so here we have the Bernoulli random variable, and once again, as we remember, the Bernoulli random variable has the probability of 0 with 1 minus theta and 1 with the probability of theta. Okay, so it's just the binary variable 0 and 1. Now let's use the example 10. Example 10. Like that. So n has the probability of 1 with theta, and has 0 with 1 minus theta, and with 1 minus theta. Given that, what we have here, each claim may be amount 20, 30, and 40 with equal probability. So let's name this value as W, and W is 20, 30, and 40. This is the value of W. Let's create the vector from that. Okay, what else? What else? We have the value, the conditional value of mean. this is theta, and the conditional variance with which is theta 1 minus theta. Okay, E and given theta, this is just theta, and variance and given theta, this is just theta times 1 minus. Okay, so these are the values for expected mean and variance of these parameters, theta and 1 minus theta. Okay, and now we evaluate the moments of theta to obtain E theta, E squared theta, to obtain what we call VHM, K, Z, and so on for our calculations. So let's start with the evaluation of moments, the E theta. Let me call ET. So what is our ET actually? Theta takes the values. Theta is the vector of 0.1, 0.8, 0.2. So I'm calculating that correctly. Oh no, which takes values 0.1 with with probabilities. Okay, we have the probabilities 0.1 and 0.2. These are the probabilities. Theta prob. Okay, and the theta values, these are 0.8 and 0.2. So the multiplication of theta times theta p will give us the sum of that value. Will give us 0.12, and this is exactly what we wanted to calculate. ET is the sum of theta times theta p. The same kind of thing can be calculated with the second moment, E of theta squared, which is 0.1 squared times 0.8 and 0.2 squared times 0.2. So ET2 will be theta p squared. And our ET2 is 0.016. Also, we are ready to calculate the expected value of W of the claim amounts, because they have equal probabilities. So expected value is just the sum of these values divided by 3. Okay, EW is W divided by 3, and sum W divided by 3. So EW is 30. This is the expected value of the claim amount. And to calculate the second moment of EW2, this will be the sum of W squared over 3. And EW2 is 966.67. So given that, we are ready to calculate the expected value of X given theta, and this will be 30 times theta. So expected value of X given theta will be 30 times theta. 30 is our EW. Okay. Then variance. What can we say about that? Variance of X given theta is this EW squared. Okay, this is it. 966 times theta times 1 minus theta. Okay, so how can we rename that? This will be variance X given data, the value of EW2 minus squared value of E theta minus that squared. So this kind of parameter, use this bracket. Okay, everything is given actually. So 966 minus 900 times theta squared. Variance will be W2 minus EW squared. Variance will be, we cannot calculate because we don't know theta so far. So this will be the theta and theta. And actually this one is also squared. Okay, so so far we try to calculate the K parameter and mu PV over sigma squared HM, and we need to somehow find out what will be our mu PV or EPV and what will be the sigma HM. Once we find that, we'll find K, and then we will be able to place this K to Z, and using Z we will be calculating the other parameters. So to start that with mu PV is 966, so it will be EW2 times what? Times this thing 0012 minus 900. This is the squared EW squared times ET squared 82. Okay, this is mu PV, and mu PV is 101.6. Okay, then sigma squared HM, sigma 2 HM. So the calculations everywhere are pretty much the same. We just need to be accurate, and that's it. So EW squared in front, and we multiply that by ET2 minus some theta P squared. So if everything okay, then 144 is the sigma squared HM. All right, now we're ready to calculate the K, which is just mu PV over sigma squared HM. And we are on our finish line for that task. The value of K is 70. Then to calculate the number of M, once again, we have only three existed values. These are 100, 200, and 250. So M is the sum of those values, and M is 550. Okay, then Z, using this M over M plus K, the Z value is 0.88. And finally, we can find the X bar. This is total claim amounts. 240, 380, and 592. This is X bar divided by M. I always forget divided by M. So X bar is 2.2. then mu x, and that's it. That's what we were looking at. So mu x is ex, and where is our ex? Where is our ex? Is it ew? Yes, it is ew. This is 30 times times 0.12. What was our 0.12? It was that sum. Okay, this is our mu x, 3.6. So the Bowman-Straub prediction for the pure premium is z times x bar times plus 1 minus z times mu x. So this is the prediction 2.36. And what will be the total claim amount? Who can say? So what value should we place over here? Anyone, please write in chat. So remember how we calculated the empty value here. So the same kind of thing will be calculated to this. Any suggestions? Or maybe formula? So it should be like what we have already thought. We multiply those values times credibility, and this is the expected number, which is prediction for total claim amount in year 4. This is 661 claims, or the claim amount. Okay, 661. This will be the expected claim amount in year 4. So this is the answer. Okay. Now what's next? Next, we should move on to the empirical applications to our credibility theory. And there are actually 3 kinds of approaches: the non-parametric approach, semi-parametric approach, and plain parametric approach. These are quite difficult to understand because they involve several theorems which are quite complex, but still the overall application is much easier than the theorem states. So let's try to solve these problems. An analyst has data of the claim frequencies of workers' compensations of 3 insurance companies. So we have these values. Let me make it larger in order for you to get the idea. So we have to calculate the Bowman-Straub credibility predictions of the numbers of claims per 100 workers for 3 companies next year. Okay. So first of all, we will need to get the idea what are the total exposures of each of the companies, and these are the 10, 11, and 12. This is the total exposure for first company, 5, 5, 6, 6 for the second, and 8, 8, 9, 10. This is for the third. And we will have the total exposures overall. Then we have to calculate the exposure weighted means of the claim frequency of these companies. That means we will, to calculate the mean, we will need to multiply 10 to 1.2, 11 to 0.9, 12 to 1.8, and so on. And this will be the exposure weighted means. Okay, let's just start doing the example 1. So A, B, and C will be the companies, and this is the sum of vector 10, 11, and 12. Then we'll have MB and MC. So here 5, 6, and 6. This is MB. And MC 8, 8, 9, 10. Okay, so this is MC. As soon as we have calculated the sum of MA, MB, and MC, the vector of that parameters, we will have the number of 90, and 90 is the total exposures of all companies. Next, we are ready to calculate the X bar A, and X bar A will be the this vector times vector of 1.2, 0.9, and 0.8. This is X bar A. Then X bar B will have these values over here times respected probabilities 0.6, 0.8, 1.2, and 1.0. And hold on, this is B, B. And the last one, 1.1, then 1.3, then 9, 7, and the initial values are given here. So X bar C. Okay. Then the numerator of MPV will be calculated like that. The numerator will be calculated like that. So it should be let me create, maybe it will be easier. PA, this is this value. PA, PV, the second one. PC, this is the third one. Okay. Then maybe we need to get rid of the sums. Let's just leave it as plain vectors, and maybe it will be easier for us to calculate. So MB and MA and BM and MC are the vectors. Okay, so the difference is between the PA and the X bar A squared times MA. So this will be plus MA times, I'm just trying, maybe it will work, maybe not, but still we have to try. And BPB X bar B, and so third one plus MC PC X bar C. Okay, so this thing object length, x bar a minus x bar a. Okay, this one is okay. This is not what I expected. We have to maintain it to the single number. So when we multiply that things, then we need to divide on the sum. We need to divide on the sum of that vector. So x bar a will be again, this is something strange. Okay, hold on. 10 times 1.2 plus 11 times. So sum of this thing. What will be the result of x bar a? That's not enough. Something is wrong. What is the sum of that? This is 33, right? So we divide by 33. 10, 11, 12, 10, 11, 12, 1.2, 0.9, 0.8. So when we multiply that, we will have 12, 9.9, and sum of multiplication. What is the sum of multiplication? 31.5. 31.5. So if we make it plain, 10 times 1.2 plus 11, 0.9 plus 12 times. Yeah, I got the point. 1.8. 1.8 over here. Okay. So this thing should work now. X bar a is 1.8. So this is 1.31. And now x bar b, we also divide by what? Divide by sum. Let me make it to the left. Sum of those divided by the sum will be 22. Here divided by 35. And maintain the sum. So we'll have the single numbers. Let's see what is unexpected here. And yeah, we need to maintain second option. Second option. Okay, and then x bar a is given, x bar b is that, x bar c is that. That's kind of okay. Then MA times PA are those. PA minus x bar b. Okay, let's try to calculate. This is calculated. Then the first thing is calculated plus the second thing also, and the third thing also. Okay, everything is calculated, and then we just need to maintain the sum of those calculations, and maybe everything will be fine. So the result is 8.22. More or less the same, but still, let's check whether we have 8, 8, 9, 10. This is okay. 5, 5, 6, 6. This is also okay. 0, 6, 0, 8, 1, 2, 1, 0, 0, 7, 0, 9, 1, 3, 1, 1. And 35 and 22. Okay. Everything should be fine. But why the sum is 8.22?